Consider a circular orbit and a central force potential V of r is equal to k divided by r to the power n, where k is greater than 0 and n is 0 to 2. If a time period of circular orbit of radius r is t1 and that of radius 2r is t2, then what is the ratio of t2 by t1? First, we can consider the circular orbit effective potential of the circular orbit is j square divided by 2m r square. J square is the angular momentum of the orbit minus v of r. This is the effective potential plus v of r, the potential experienced by the planet. J square 2m r square. So v of r is nothing but k divided by r to the power n. If the circular orbit is stable orbit, the derivative of the effective potential goes to 0. We can take the derivative though v divided by though r, this is effective potential, should goes to 0. If you are taking the derivative of this one, j square divided by 2m r cube, so minus it will come here, you have to multiply with 1 2 plus n k r to the power n plus 1 is equal to 0. 2 2 will get cancelled, minus j square m r cube n k r to the power n plus 1 equal to 0. We can find the angular momentum. Angular in terms of that quantity, angular momentum should be equal to r into p or r into mv or r into r square m omega. This is the angular momentum quantity. We can substitute here orbital angular momentum m r square omega divided by r cube whole square plus n k power k divided by r to the power n plus 1 equal to 0. Now take the square of this one. I am doing it here, minus m square r power 4 omega square divided by r cube plus n k r power n plus 1 equal to 0. Rearrange this equation, r cube r get cancel. So m square r omega square equal to minus n k r power n plus 1. Omega square equal to minus n k r power n plus 1 divided by into r. M will also come, m square, there are no other quantity, so omega square should be equal to minus n k m square 1 divided by r power n plus 2, or else omega is proportional to 1 divided by r power n plus 2 divided by 2. If you are taking the square root on both sides, it will become, this is constant, k is constant, n is number, it's 0 to 1 sum of constants, m also mass of the planet also constants. So the time period is inversely proportional to the angular frequency, is proportional to r power n plus 2 divided by 2 or proportional to r power n by 2 plus 1. Now this is a time period relation. Time period is proportional to r power, the radius power divided by n plus 2 plus 1. Now come to our question. If the time period of the circular orbit is of radius r is t1, that of radius 2r is t2, then what is this ratio? So the time period of the circular orbit t1 is r. Then we can substitute this condition in the final result. First we can find the time period of the orbit r is t1. So t1 is proportional to the radius is r whole to the power n by 2 plus 1. Time period of the orbit t2 is proportional to 2r. The radius is 2r, n by 2 plus 1. They are asking what is the ratio T2 by T1. If you are taking the ratio, the constant will get cancelled. The proportional will become equal. Some constant sitting in front of the constant will get cancelled. T2 is proportional to 2r whole power n by 2 plus 1 divided by T1 is proportional to r to the power n by 2 plus 1. It's a common power, so T2 by T1 is equal to 2r by r whole power n by 2 plus 1. R will get cancelled. T2 by T1 equal to 2 power n by 2 plus 1. This is the answer. Given option is 3.